Yeah, so we've just heard a really interesting presentation by Kevin and his advisor about a particular, cognitive architecture and what you call a proto AGI system. And the situation in the field now obviously is nobody has achieved human level AGI yet, and there's different approaches which have different strengths and weaknesses, and this is just where the field is at. It's not a bad place to be at, and with the greater processing power and data and the software libraries for performing basic AI tasks, one can now more easily get to the bottom line of what a certain architecture can do or can't do via experimentation, and look at the intersections between different architectures. And this sort of empirical work is quite valuable, and what I spent a lot of time on with my team in Singularity and OpenCog. However, I think it's also interesting to take a step back and think about the deeper theoretical basis of what we're doing with all these different AGI architectures. And if you take the analogy to flying machines, which is well worn and imperfect, but still there's something there. I mean, there's a lot of different ways to make machines that fly, right? There's machines that flap like birds, which actually work better now than they did a couple of decades ago. There's helicopters, there's airplanes, there's dirigibles, there's spacecraft. There's also fluid dynamics and aerodynamics, which is a general theory that underlies all these different types of flying machines. And of course, the Wright brothers didn't derive their design for an airplane using the Navier-Stokes equation of fluid dynamics. On the other hand, now the modern design of military aircraft is a mix of theory and experiment. And in the AGI context, we're egregiously matching. We're missing our Navier-Stokes equation, right? We're missing the equations of intelligence that underlie all the different AGI architectures, explain their different strengths and weaknesses, and give you guidance about how to build new architecture. So I've always been sort of divided in my mind as an AGI researcher as to how much time to spend developing, designing, experimenting with particular architectures to see what they can do, sort of trying to be the Wright brothers, versus how much time do you spend trying to be Navier and Stokes and figure out like the basic equations of movement and structure of intelligence? Because if you understand the theory better, perhaps designing architectures can become a more straightforward process. So I've obviously been spending more time on the practical side, if you give practical a very broad definition, at least of spending more time on theoretical, conceptual, architectural developments related to building particular systems that do particular things, like the OpenCog Proto AGI engine, Singularity Net platform for making OpenCog and other AI systems decentralized and so forth. But in the background, I've been ongoingly thinking a lot about what ingredients would you need to put together to create a general theory of general intelligence. And so what I want to talk about now for the next 20-25 minutes is I want to give a brief run through of some of the ideas I've been exploring in the direction of a general theory of general intelligence, and then explain how some of these ideas are guiding, sometimes loosely, sometimes more formally, guiding the work that Alexei and a bunch of our other colleagues in SingularityNet and OpenCog, the work that we're doing toward creating a new version of the OpenCog architecture. So yeah, to be clear, the theory that we're looking at here is intended to be, as general as we can make it. I mean, of course, if you have a mind 80 billion times as intelligent as humans, it may think all of our theory is completely primitive and ridiculous. But at least in aspiration, we're looking for principles of intelligence that can apply to human and non-human systems and to systems that are beyond the human in some sense. And there are various threads of inquiry we can draw on in creating a general theory of general intelligence. I mean, most participants here are already familiar with Marcus Hutter's universal AI theory, which is certainly interesting and relevant, and tries to solve the problem of, how would you make a system that could maximize computable reward functions in computable environments. And Hutter gives an algorithm that's about as good as anything at doing that if you give it enough resources. And that's interesting. I mean, there's the formulation of the problem in terms of reinforcement learning is arguably limiting in some ways. And there's a question as to whether what works with essentially infinite resources is that relevant to what works with realistic resources. But it's an interesting potential starting point for investigation. Of course, neuroscience is another potential starting point, and at least at the level of inspiration has proved valuable. Current neural nets have little to do with actual neuroscience, but they were inspired originally by neuroscience. But of course, neuroscience is insanely complicated. Like this little graph I'm showing, each of the little boxes is a different brain region studied by neuroscientists, and the links are connections between the brain regions. So there's a kind of specific architecture underlying how the human brain works at the intermodule level. Then there's so many neurons and neurotransmitters. So there's a lot of lessons to be gained from the human brain. And one problem is how to emulate what the brain does in a different kind of hardware, given our limited ability to image the brain right now. Another problem is extracting what's particular to the human animal from what is a general principle of intelligence. Cognitive science is another approach, and Kevin's talk that we just saw now is an attempt to sort of come to the computer science and practical AGI world from the point of view of human cognitive science, really, and looking at the different kinds of cognitive processing a human mind does. And cognitive science has isolated the different parts of a human like mind: long-term memory, short-term memory, perception, action, language, deliberation, metacognition, and so forth. And so even if you don't want to take exactly how the brain works as a guide for how an AGI should work, you could take the information processing characteristics of the human mind. We're going to hear in our one of the panel discussions on Friday of this conference from David Weinbaum and Kabir Vetas have been working out a totally different way of thinking about intelligence. What could you think of as open-ended intelligence? Thinking of an AI not as optimizing a reward function, but as something that self-organizes, creates and processes patterns within itself and its environment, where goal functions and rewards are among the patterns that may pop up and then get improved or go away within the self-organizing system. So this is more looking at AGI as part of the study of complex self-organizing systems. So all these threads, all these points of view on general intelligence, I think are important. And these are all themes that I've pulled together in a series of fairly sketchy theoretical papers over the last decade or two. So I made a blog post on my personal blog, The Multiverse According to Ben, last month on the general theory of general intelligence. And pretty much that blog post is a bunch of links to papers published in various conferences and journals, and a couple I just posted online over the last decade, but just trying to explain how they sequence together and contribute together to an overall theory. And what I'm going to do now is spend a few minutes almost just listing some of the highlights of the ideas in those papers, because there's too much. I mean, eventually I'll turn that into a whole book once I have time to fill in more details. There's too much to go through in detail in a brief talk. So I will list through some of the particulars in those papers and then explain how those are feeding in our current design and thinking process as among the ingredients that we need to create a new open code architecture. So on a philosophical level, among other things, we could say an intelligent system, a mind, is a self-organizing pattern system that's engaged in recognizing patterns in itself and its environment, including critically but not exclusively patterns regarding the impacts that its actions tend to have. And it's not just recognizing, it's building new patterns in itself and in its own environment. Of course, the patterns it recognizes feed into the patterns it builds. And this high-level way of looking at things, of course, relates to open-ended intelligence and also explains how a practical system can optimize computable reward functions in computable environments. So what is a pattern? So this is in itself a complex, both philosophical and and technical question. One line of thinking I've been playing around with lately goes back to some philosophy and math work by Spencer Brown and Laws of Form, and a bunch of follow-ups of that work by Lewis Kaufman. And I'd encourage you to look at his website at the University of Illinois, some amazing stuff intersecting knot theory, quantum topology, and then sort of the phenomenology and ontology of perception and how the mind works. But the core idea that they have is we want to start with just the process of distinction. Start with the process of a distinction that distinguishes one thing from another, and they try to build up an entire model of the mind from distinctions of distinctions of distinctions, which is quite philosophical, but one can use this as a way to ground the concept of pattern, which is then something practical. So I mean, if you have a certain set of distinctions you care about, a certain set you don't care about, and then you have a program F that makes some distinctions among its inputs, meaning it maps some inputs into the same output and some into different outputs, then you can say that a program P or a process P, if you're looking beyond programs, a process P is a pattern of process F if P makes every relevant distinction F does, but makes fewer distinctions overall. And you can show that this definition, it's under some assumptions, it's equivalent to the algorithmic information theory view of patterns, which says basically a program is a pattern in a bit string if it produces that bit string, but is shorter than that bit string on the chosen reference machine. So we can generalize this to quantum computing. I'm not going to go over this for time reasons, but this is in one of my papers, one of my technical papers for this conference, which you could find in the proceedings. You could look at distinctions that are weighted with amplitudes rather than being binary or fuzzy, and come up with quantum theories of patterns. And I was pursuing this line of thought partly because I've been thinking for a while about what would you consider a really natural underlying computational model for general intelligence. I mean, there's a lot of computational models that are equivalent under bisimulation in computer science, right? So you have Turing machines with their tapes, you have combinatory logic, and you have a whole bunch of formal languages, a whole bunch of other things that you study in theoretical computer science, and different ones are different for different reasons. And I was trying to go back to basics in terms of patterns and distinctions to see what would be a computational model that would be highly natural in terms of AGI. This paper, Combinatorial Decision DAGs, is in the proceedings of AGI conference, and I have a separate talk on this in the main AGI conference later this week, so I don't want to go in in too much detail, but it feeds into the more general points I want to make. So I want to say something about it. The basic idea here is you start with a decision tree representation of a function, and this is not that weird. I mean, in computational complexity theory, you use decision tree complexity, the complexity, the size of the decision tree representation of a function as one way to measure the complexity of that function. But then I look at decision trees that are recursive in the sense that you can encode a decision tree as, for example, a bit string and feed it into another decision tree. So you have decision trees that make decisions based on other decision trees. And then you introduce a type of pattern-based memoization in a way, where if you have two sub-decision trees, and then you have you have a small process or a simple process that can map one decision tree into another one. So this decision tree doesn't have to be the same as that one, but it can be produced by some compact function from that one. Then you could replace a decision tree, say replace decision tree X with decision tree Y, well, with a function that produces X from decision tree Y plus a pointer to decision tree Y. So if you if you introduce that kind of pattern-based memoization and recursion among decision trees, then you get something that's pretty much like the SK combinatory logic on decision trees, and you get a different sort of computational model which has some interesting properties. So there's a there's a way of measuring entropy which is different than Shannon entropy called, that's not it, it's called, I don't have a slide for it, but let me explain it. It's called logical entropy. So the logical entropy of a partition is simply the percentage of pairs of elements that are put in different partition cells. So if you have a partition of n elements into 5 cells, there are n squared possible pairs of elements. What percent of those pairs are put in different partition cells rather than the same one? That's the logical entropy. And there's a generalization of that called graftropy, which is in a paper that I have on arXiv, which deals with the case of a subjective observer making distinctions between things. So in the case of graftropy, you have a partition, you have a distinction graph where two observations, for example, represented by nodes in a graph. They have a link between them if some observer cannot distinguish the two of them. So then a partition is a distinction graph, which is divided into a bunch of disjoint subgraphs that are complete graphs. So the graftropy is just the percentage of all possible links between nodes in a distinction graph that are present in a certain graph. But anyway, what's interesting is in this combinatorial decision graph computational model, which I go over in my talk in the main AGI conference thread, if you make a program bigger, it doesn't decrease the logical entropy. And on average, bigger programs have higher logical entropy. So one of the math properties I liked about this particular representation in terms of patterns and combinatorial decision trees is there's a very natural, straightforward connection between the programmatic representation and the entropy if you look at logical entropy rather than looking at Shannon entropy. So I'll say more about why this is interesting a little later. And yeah, this was the paper on graftropy, which is on arXiv. So this connection between program representations and entropies is interesting and goes deeper, and it has to do, among other things, with the understanding of causality. Like one of the weaknesses of a lot of what's done in machine learning now is it's heavily correlative. I mean, you're finding patterns in data, and you're not in general seeing equally powerful ways of understanding the causal structure of data. And of course, there's a whole bunch of interesting work on that in the last few years. most famously, Judea Pearl's ongoing fleshing out of causal networks and as a generalization of Bayes networks, but a lot more beyond that. Now, there's also some interesting work on algorithmic Markov conditions. So pretty much everything you can do with causal networks using probability theory and then information theory, you can also do with algorithmic information theory. So just as, say, in a Bayesian network, you want a node that's independent of its ancestors conditional on its parents. In algorithmic Markov network, you can look at a graph with bit strings at the nodes, where the bit string at one node has no extra compressibility conditional on its ancestors beyond its compressibility conditional on its parents, right? And so that's if you construct an algorithmic Markov tree like this, you can look at causality in a different way, where you can even infer, or at least you can hypothesize causality based on very, very few data points. And this relates to one-shot learning and few-shot learning and so forth, because to gather the statistics needed to make a traditional sort of Markovian network to measure causality, you can need a lot of observations. And if you can just look at mutual compressibility between bit strings or other computational representations and guess at causality that way, I mean, then you can make do with many, many fewer examples. I mean, of course, there's a lot more subtlety underlying that. But yeah, I had a paper on the maximal algorithmic caliber principle, which is similar to the maximum caliber principle, which is the temporal version of Jane's maximum entropy principle. So you can look at, just as natural systems tend to maximize entropy given their constraints, in some sense, do cognitive systems maximize algorithmic caliber, which is the generalization of maximum entropy to systems progressing over time, but to looking at entropies between individual observations rather than statistical ensembles. So there's a whole line of thinking there connecting together statistical information with algorithmic information. And I think at bottom, when you sift through a whole bunch of annoying mathematics and cognitive architecture, this has a lot to do with the neural and symbolic connection, because a lot of what's being done with neural nets now is really statistical analysis. It's really information theory based, and symbolic systems, whether they're cast as logic or program learning or whatnot, these symbolic systems, they're doing things that are related to algorithmic information and compressibility when you dig down. So the relation between information entropies and logical entropies and then algorithmic information, this relation foundationally tells you a lot about how neural and symbolic connect with each other. And I'll say more about that in a moment. I mean, I'm short on time, so I won't go through this in detail, but I had a blog post recently sort of looking at algorithmic Markov conditions and how these connect with decision theory. I mean, there's a one of the many decision theories out there is causal decision theory, which says you should choose the action that will cause the best outcome for you. And there are various paradoxes associated with it. And I think many of them go away if you interpret causality correctly in terms of algorithmic Markov condition or its generalizations. I mean, you can also pursue similar math to ask, what sorts of, if a system, an AGI system is viewed as pursuing goals, what sorts of goals should it be pursuing? And you can look at intrinsically which sorts of goals can most efficiently be pursued by an intelligent system, and introduce notions of goal coherence. Say a goal is coherent if achieving that goal over a whole system is consistent with achieving the system's goal relative to the parts of that system. So like is achieving your goal over a long time period the composition of achieving your goals over the shorter time periods comprising that longer time period. So I'm I think I haven't posted my thoughts on this yet, but I will later this week. They're sitting on my hard drive. But I just include this here to indicate that you can't really think about the goal is just something given and arbitrary, and then the AGI system is just trying to maximize an arbitrary goal. I mean, AXE looks at it that way. You can look at it that way, but I think there are certain symmetries and mathematical and conceptual properties of goals that make them sort of more copacetic to real world AGI and match better with AGI systems. So you can think about goal optimization as an important part of intelligence, but you then need to be thinking about properties of goals as well as properties of the optimizing system. So before briefly jumping into OpenCog 2.0, so one concept that comes out of all this is what I called cognitive synergy. And cognitive synergy is basically the idea that sometimes an AGI system may want to have multiple different representations of itself and its world, and then different learning algorithms correspond to these different representations. And then it needs good interaction between the different learning algorithms corresponding to different representations. So it needs, so when it gets stuck with learning regarding one representation, it needs to be able to invoke learning regarding another representation to get it unstuck, which requires sort of sharing of intermediate learning processing states between the learning algorithms working on the different representations. And why that's relevant? Well, one reason it's relevant is just because of the nature of the particular kind of intelligence that humans are. So human beings are pretty general intelligences, probably more general than like coffee cups or rats and so forth, but we're not maximally general intelligences. We can't run a maze in 750 dimensions very well, but we're not AXE. And some years ago, I published a paper called The Embodied Communication Prior, which had an intent quite similar to Yoshua Bengio's more recent paper on the consciousness prior. I didn't choose as sexy a name as Yoshua did, but I mean, I wanted to keep the qualia problem and the philosophy of consciousness off to the side, because what I was after here is what are really the biases that human beings evolved for. I mean, you can say being human, but that's too general. It seems like our general intelligence, it evolved for existing and manipulating solid objects in a world obeying certain kinds of laws of physics. We're not intelligent gas clouds in Jupiter. We're manipulating solid objects and breaking and composing them, and we're controlling individual bodies. Each of our minds is stuck in one body. What do these bodies do? Well, they manipulate solid objects. They move around, and they also communicate with other similar bodies that are controlled by similar cognitive systems. So I think the fact that our intelligence evolved for this communication among groups of similar minds in a world where the similar minds are manipulating, a shared collection of common solid objects that they can move around and manipulate. I think this has a lot to say about how general intelligence processes are kind of simplified into humanish general intelligence properties. And you can look at the situation that we evolved for, and you can see how the kinds of memory characteristic of the human mind come out of that. So you can look at semantic memory, procedural memory, sensory memory, attentional memory, and so forth. And these various aspects of human memory that are concretized in the human brain by different sub-networks specialized for those types of memory, these different types of memory, they basically correspond to different aspects of embodied communication, which is what we evolved to be biased to learn. But then these different types of memory correspond to different learning algorithms. And in the brain, when you say different learning algorithms, I mean, that can mean a lot of different things. It can mean different architectures within microcolumnar structure within different columns and different parts of the cortex. I mean, it can mean different distributions of different types of neurotransmitters and different sorts of synapses and types of neurons in the OpenCog architecture, what it means is declarative memory and reinforcement learning, sensory memory, episodic memory. To an extent, we have different algorithms corresponding to these, and they all need to interoperate. So going back to the very beginning of this talk, what we're looking at in OpenCog is an architecture that is inspired by human cognitive science, less so by neuroscience. And within each of the sort of modules of mind identified by human cognitive science, like say declarative semantic reasoning, sensory processing, reinforcement learning, attention, episodic, within each of these modules that is highlighted by human cognitive science, I mean, then we're trying to use computer science and math to figure out the best algorithms to deal with learning relative to those modules. And the cognitive synergy idea comes in the interoperation and common representation among these modules. So if you're using, say, a probabilistic programming method for procedure learning and a logic engine for declarative learning and reasoning, how do these interact with each other? When the logic engine gets stuck, can it share its intermediate state with the probabilistic programming engine to help it get out of where it was stuck by translating the declarative learning problem into a procedure learning problem? Or when a neural net gets stuck on perceiving something, is it just stuck, or can it send elements of its intermediate state to a probabilistic programming procedure learning engine or to a logical reasoning engine to help it overcome its perception problem? And one can formalize this in terms of category theory, in terms of morphisms between the categories characterizing the different types of knowledge and the corresponding different types of processing, which is done in this paper from AGI conference. Looks like it was 2017, the one in Australia a few years ago. Now, this general theory of general intelligence, you could take in a bunch of different directions. I mean, if there's anyone out there who's really crazy, you could look up a paper I posted called Uri Physics, which tries to explain this, use this line of thinking regarding general intelligence in a very, very general philosophy of mind way, just to explain how minds work. But the direction I want to take in the last few minutes I have here before going to questions is just giving a clue of how all these abstract ideas are guiding our practical work on OpenCog. And I'm going to mostly leave this to discussion, but spend just a couple minutes going over some key points. So, I mean, OpenCog is one in a series of AGI systems that I've been experimenting with over the last few decades. The oldest code in OpenCog goes back to maybe 2001, although hopefully all the code I wrote has been removed and improved by now. I haven't been coding much for the last few years. We open sourced this in 2008, and the core idea here is to realize this notion of cognitive synergy by having a common representation among different AI algorithms that correspond to different types of memory. So the common representation is what we call the Adams space, which is a weighted labeled hypergraph knowledge representation, or you could more accurately call it a metagraph, because a hypergraph is like a graph where the links can go between many nodes. But here we also have links that can point to links, or links that can point to whole subgraphs, which some folks have called a metagraph. I'd call it a generalized hypergraph. But you have this common Adams space knowledge store, and then different learning algorithms corresponding to different types of knowledge all use this common Adams space knowledge store to represent their knowledge. And by working out the knowledge representation within this hypergraph appropriately, using the correct collection of type systems, you can get it so that when one algorithm needs help or needs acceleration, then the knowledge that it's represented in the Adams space can be transformed into the sort of knowledge in the Adams space that another learning, reasoning, or intelligence algorithm needs to help out that first algorithm. So we try to foster cognitive synergy among different AI algorithms by having the different AI algorithms use representations that overlap and are easily intertransformable due to using the same underlying Adams space meta representational fabric. And I mean, this can be used in more of a reinforcement learning vein. It can be used in more of a self-organizing systems, open-ended intelligence vein. And to get human-like intelligence, I think you need both. I mean, you need a certain element of goal-oriented activity where the system is trying to figure out what procedures will let it achieve its goals in the relevant context. And you need a certain amount of just ambient self-organizing learning where the system is recognizing patterns in itself and its environment without an explicit goal in mind. And OpenCog supports all these. It's been around a while, and we've been doing a lot of different things with it. We certainly haven't achieved AGI with it yet. We've been doing some prototype experiments of various sorts aimed at AGI, and we've also been using OpenCog within some narrow AI commercial applications, sort of buried on the back end, which has been interesting. And we've hit some obstacles in our recent work with OpenCog, which is pushing us toward, planning and designing a major rewrite of key parts of the system. I mean, it could be throw it all out, complete rewrite from scratch. Probably it won't be that, but there's going to be some deep improvements to various parts of OpenCog. Sort of tongue in cheek, we've been thinking of this as OpenCog 2.0, but that's a bit of a joke because the current OpenCog is more 0.2 than 1.0 anyway. But we've also been thinking of this as a true AGI engine, just because having a new name is nice. And I mean, there's a bunch of things that we need to do here. I mean, we need to upgrade the atom space in serious ways. We need to make the atom space as a body of code more scalable across many different machines and able to better exploit parallel processing on a single machine, and some more technical improvements to how types in the atom space work that I'll talk about in a moment. We need to better integrate modern deep learning frameworks and toolkits with OpenCog atom space, so that, among other things, you can efficiently and cleanly implement, for example, a common probabilistic programming framework across the atom space and across something running in, say, TensorFlow or Torch and so forth. And from revising the atom space, the common weight-labeled hypergraph representation at the center of an OpenCog type architecture, I mean, that will imply some changes to the various AI tools that we have now working on the atom space. So the main goals of revising the OpenCog atom space are to make it easier to make the thing massively scalable. I mean, you can now run an atom space across many machines, but we have no feasible way to run it across like 10,000 machines. But clearly, you will need to do that to make an AGI. The scripting language we use for manipulating the atom space now has some problems with it, which are understandable given that it sort of evolved accumulatively over many years of use. We're now sort of scripting in a mix of Scheme or Python or C++ and explicit node and link operations, and we need something more coherent, where you're just using one language that the AI is using, which is cleanly transformed into one language that humans are using, rather than a mix of sort of Atomese and Scheme or Python or something. And yeah, we need to better integrate both neural symbolic interaction with external neural net libraries and meta reasoning, where you're learning about different node types and link types and type systems and so forth. And all these things could be done in principle with the current OpenCog atom space system, which is highly flexible, but at a certain point it seems like it can be easier to go back and revise things. So one key element here is supporting probabilistic logic and programming better. And I don't have time to go into this much, but I mean, there's a lot of mathematical commonalities between what you do in probabilistic logic on declarative knowledge, like in our PLN probabilistic logic system, what you can do with probabilistic programming for automated program learning, and then what you do in probabilistic learning across neural net architectures. As you can see, in primitive form in things like the Edward framework for probabilistic programming across neural nets, but you need to do much more general learning than these have done. So there's a common probabilistic learning framework you can see across program learning, logic, and neural net training and architecture learning, but to cash out that mathematical similarity in a scalable way that is suitable for real-time application and real-world experimentation, that has a lot of difficult implications for the infrastructure of your system. And OpenCog right now isn't up to that, but neither is anything else, actually. So, I mean, we've been doing a lot of work with neural symbolic integration. If you look at Alexei Potapov's paper on cognitive modules from a previous AGI conference, you see how in some ways you can go beyond just using a neural net as an input or output device for a symbolic system and deal with manipulation of, say, the processing graphs in a torch neural network and within various OpenCog nodes. But we need to go deeper in the integration, and this is both it's a software issue and a conceptual issue. And you'll see in one of my other co-author papers in this AGI conference, one of the many ways we're trying to make neural symbolic integration of work in a deeper way. Here we're looking at vector embeddings from an OpenCog hypergraph using an extension of the deep walk algorithm, and we're doing that now. But this sort of thing can be done, with more depth and more efficiency with some revisions to the architecture. Another thing I've wanted to play with for decades is algorithmic chemistry, which is like programs that rewrite programs to make other programs. And you can use an OpenCog atom space as this sort of underlying algorithmic chemistry infrastructure for a primordial cognitive soup of intermodifying algorithms, which can be an amazing way to foster computational creativity and feed new inputs to reasoning and learning algorithms. But again, I've tried to fiddle with this in current OpenCog code base. It's just very, very slow. So if we look at the high level architecture we want here, I mean, we have distributed atom space, which lives across many, many machines. We need a local cache atom space, which is something more like the current atom space. It works pretty well on one machine. You need some funky middleware to mediate between various local cache atom spaces and a distributed atom space. You're going from the distributed atom space to embedding vectors and to symbolic patterns recognized by pattern mining. And we have a workshop on, among other things, pattern mining in OpenCog on the atom space in this AGI conference. Then we have an Adamese language interpreter, and this is one thing we're deep in the process of rebuilding now, which is a sort of native language of this atom space. And then using this Adamese language, you can either implement AI algorithms or you can implement appropriate interfaces to external libraries like neural net toolkits where AI algorithms are implemented. So, I mean, at the high level, this is more a software architecture than an AGI architecture, but it's a software architecture designed to implement the cognitive synergy based AI approach that I've very roughly alluded to. So here this is a list of questions from another of my papers for this AGI conference, and the paper is called "What properties should a programming language for an AGI have?" Right. So, and programming language is not the only thing we need to do here, but it's an interesting way to crystallize many of the broader questions. So what do we want out of an Adamese language, which can serve as the infrastructure via which all these different AI algorithms dealing with different kinds of learning and different kinds of memory update and learn from it and grow this shared knowledge hypergraph? Then what should the language be on the surface level that humans could read and edit and write, but also what happens in the guts of this? And this is part of what led me to think about combinatorial decision graphs I was talking about 25 minutes ago, because you use combinatory logic deep in the guts of a Haskell interpreter and so forth. So the intersection of sort of combinatorial logic with pattern theory and simplification, which is what you see inside combinatorial decision graphs. These, I think, can be some of the structures useful deep inside the guts of an Adamese interpreter. But then it gets quite subtle when you think about type systems. I mean, clearly you want dependent types, and you probably want linear types, which take into account resource utilization, and you want probabilistic types. But given that we still don't really know how to build an AGI yet, we can't expect to find one dependent probabilistic linear type system to rule them all and just wire it into the atom space. It's going to have to be more like different learning algorithms dealing with different types of knowledge have different type systems, which are especially corresponding to the types of learning reasoning that they need to do. And then the atom space has to be a sort of meta infrastructure that lets different algorithms have different type systems that can interact and be refined in the course of learning. And this leads you to a sophisticated sort of gradual typing. So you need Adamese to be a gradually typed language supporting, probabilistic and dependent higher order types. And this is quite interesting because gradual typing maps via Curry-Howard correspondence into paraconsistent logic, and our PLN logic is a paraconsistent logic, which a probabilistic paraconsistent logic, which may be suitable for reasoning about this type of gradual type system that we want to use underlying Adamese 2.0, which is an interesting sort of metacognition. Now, doing all this super fancy probabilistic functional programming stuff doesn't seem like it could be efficient at all. I mean, the saving grace is sort of the programming language execution may not be the slow part, because getting knowledge in and out of a massive distributed hypergraph may be even slower, so that you can afford to do some fancy stuff in the language level. But anyway, these are hard questions which we're wrestling with now. And it's interesting, these are really quite different questions than the ones people are wrestling with in the corner of the AGI world, where they're looking at, how do you scale up deep reinforcement learning networks over as many machines as possible to play video games or to simulate understanding of natural language in a system that doesn't really understand it. So I mean, we're proceeding here from what I think is a pretty thorough and sophisticated theoretical understanding of what general intelligence is, what human-like general intelligence is, as a sort of specialization of more fully mathematical general intelligence. And then how would you build an algorithmic framework that could efficiently encompass the diversity of learning and reasoning that you need to realize human-like general intelligence within feasible resources? And we certainly don't understand everything that we need to do this, but this is a snapshot of some aspects of where we're at now anyway. And I apologize for going on too long as I usually do. I was talking as fast as I thought I could and still be understood. But yeah, let's move to questions and discussion now.